Assalamualaikum class and salam sejahtera. In this lecture, we continue to the second part of this chapter. So this chapter is chapter number 7, graph, and in this lecture, we start with this topic discussing about new graph from old graph. That means we want to produce a new graph from existing graph. In the graph model for the large network, the vertices corresponding to the computer centers other than the interest, means other the involved vertices. So these vertices can be removed. Then all edges incident with a vertex that was removed also can be removed. Then when edges and vertices are removed from a graph without removing endpoints of any remaining edges, then we can obtain a smaller graph from the original graph. So this smaller graph is referred to as subgraph. So let's see what is the proper definition of subgraph. A subgraph of a graph G. Okay, so the original graph is G, is a graph denoted as H. Okay, denoted as H with two sets W and F. Okay, the original set G or the original graph G containing two sets V and E, where the set V containing all the vertices for the graph G and the set E containing all the edges for the graph G. While for the subgraph H, it has two sets also. It has W, which containing all the vertices for the graph H, and set F containing all the edges for the graph H. Right? Because H is a subgraph of the graph G, then the set W is a subset of the set V, and the set F is a subset of the set E. A subgraph H of the graph G is proper subgraph if proper subgraph of G if H is exactly equal to G. Then we can say that H is a proper subgraph of G. Okay, remember, in graph also we are dealing with sets. Given a set of vertices of graph, a subgraph of this graph with these vertices and edges of the graph that connect them can be formed. So let's consider definition number 2. Let G equal to VE be a simple graph. The subgraph induced by a subset W, okay, a subgraph induced by a subset W is a graph H with sets W and F, where the set W is a subset of the set V of the original graph. And the other condition is the edge set F. The edge set F contains an edge in E if and only if both endpoints of this edge are in the set W. Then we can say that H is a subgraph that induced by the subset W. I'll give you example. Okay, so in this example, the main graph or the original graph is K5, while the subgraph of this graph is G. So let's see why. We are referring back to the definition. So we do it one by one. From K5. So K5 is equal to V E. Alright, where V is a set containing all the vertices of K5. So we have a we have a B, C, D, and E. Right? So about E. E containing all the edges. Okay, let's count how many edges. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I think we cover all the edges. No, 9 and another one, 10. Okay, we have 10 edges. So we denote as E1, E2 up to E10. Alright. While the other side we have G. Graph G, let's say graph G contains W and F. So with the set W containing all the vertices, so the remaining vertices after we remove D, the vertex D, so the remaining vertices are A, B, C, and E. And for the set F, we have edges. Let's say E1, how many? 1, 2, 3, 4, 5. E2, E3, E4, and E5. So clearly we can see that, okay, W is a subset of V and F is a subset of E. So that is why we say that G is a subgraph of the original graph K5. Alright, removing or adding edges of a graph. Okay, we start with edges. So for the edges of the graph, we can add, we also can remove edges from a graph. Given a graph G equal to VE, so an edge E which belongs to the set E, okay, we are given two information. The first one is the graph G, and we also given an edge E. Then a subgraph of G can be produced by removing the edge E. Alright, so the original graph is G. So if we remove single element from the set E, means we remove single edge from the set E, then we can obtain a new graph. So this new graph is a subgraph of graph G. Alright, so the resulting subgraph denoted like this, G minus E. So G minus E is a graph. Okay, it's a graph because it is a subgraph. So this subgraph has the same vertex set V because we don't do anything. We don't add or we don't remove any vertex from the set V. It still remains as the original V. But for the set E, so we remove an edge from E, which is the edge E, the small e. So we have minus E. Alright, minus E. So how to denote the new subgraph? So the subgraph is denoted as G minus E, which is equal to V, which is the original vertex set. And for the edge set, we have E minus the entry E. This is set minus set. Okay, because we are dealing with set. So E is a set minus, this is another set with single entry, which is E. Okay, so that is how we denote the matrix notation properly. Similarly, if E prime is a subset of the set E, a subgraph of G can be produced by removing the edges in the subset E prime from the graph. So this time you are given another set E prime, which is subset of E. Okay, subset of the set E. By removing all entries from the subset E, so we can produce another subgraph from the graph G. So this new subgraph is denoted like this, G minus E prime. Alright, so E prime is the entire subset E prime. It is equal to V because V still remain in its original form, and the changing is only to the second part. Okay, for the second part, we have E, which is the original edge set, minus E prime, which is the subset of the edge E set. Alright, so this is a new graph, which is a subgraph of the original graph G. An edge E also can be added, okay, other than removing E. Okay, we also can add E to a graph to produce a new graph. And this graph, of course, it is larger than the original one because we add a new edge to it, right? A larger graph when this edge E connects two vertices already in G. The new graph produced by adding a new edge E. Previously, we removed E, so we have minus E. So this time we add E, so we have plus E. Adding a new edge E connecting two previously non-incident vertices. Okay, in the original graph G, these vertices are not connected. They are not incident. But after we add a new edge E, so this non-incident vertices now becomes incident or becomes connected. Okay, so to the graph G is denoted as G plus E. Hence, G plus E is a new graph. It is a subgraph of G. So G plus E equal to V. V remain in its original form. So the changes it at the second part. So we have E union set E. Okay, E is a set union. This is a new set which is containing only single element H E. Alright, so this is a new subgraph of the graph G by adding an H to it. The vertex set of G plus E is the same, okay, as the vertex set of G, and the H set is the union of the H set of G, which is the original graph, and also the added H, which is a set with single entry E. Alright, so previously we're dealing with edges. Now we are dealing with vertices. Removing vertices from a graph. Okay, similarly we also can remove vertex or vertices from original graph. When a vertex V and all edges incident to this vertex V are removed from the graph G, then a subgraph which is denoted by G minus V is produced. Originally, we have a original graph G. Then after we remove a vertex V, okay, then we have a new graph which is a subgraph of G denoted as G minus V. Observe that the subgraph G minus V is equal to V minus a set containing single entry V. Right? This is a set. This is also a set. Okay? Equal to E prime. Why it is a E prime? The changes only made on the vertex set. So what happened with the edge set? Of course, after we remove one vertex, we also need to remove all the edges incident with that remove vertex. So that's why the changes also happen to the set E. Okay, because a few edges removed together with the vertex V. So that's why we have E prime instead of the original set E. Where E prime is the set of edges of G not incident to V, because all the edges incident to V have been removed. Similarly, if V prime is a subset of V, alright, so we have V prime, which is another set of vertices, which is subset of V. Then the graph G minus V prime is a new graph. Okay, it is a new graph which is a subgraph of the original graph G. G minus V prime is a new graph which is equal to V minus V prime, the original set V minus the subset set V prime, and the edges is E prime also because we remove all the edges incident to the removed vertices. Okay, so this is a subgraph of the original graph G, where E prime is the set of the edges of G not incident to the vertex in V prime. Graph union. Now we can combine two or more graph together and come out with a new graph. Two or more graphs can be combined in various ways. The new graph that contains all the vertices and all the edges of this graph is called the union of the graph. Okay, so consider definition number 3, the union of two simple graph G1 and G2, where G1 equal to V1 E1 and G2 equal to V2 E2. Alright, so the union of these two graphs is the simple graph. With vertex set is equal to V1 union V2 and the edge set E1 union E2. So the union of G1 and G2 is denoted as G1 union G2. Originally, we have two different graphs, G1, G2. There are two different graphs. So after we combine together, so we can obtain a new graph. It is denoted as G1 union G2. Since it is a graph, So since it is a graph, so we need to put parentheses here, okay, where the first element is representing the vertices set for this new graph, and the second element representing the edges set of this new graph. So the vertices set for this new graph is V1 union V2, while the new set for the edge for this graph is E1 union E2. Okay, that is how we combine two graphs together using union operation on sets. The vertex set of the union G1 union G2 is the union of the two vertex sets, okay, namely A, B, C, D, E, F. Okay, A, B, C, D, F. The edge set of the union is the union of two edges set. The union is displayed below. Okay, originally we have a G1 with vertex set. Okay, G1, V1, E1. And we have G2, V2, E2. Okay, so for V1, we have A, B, C, D, E. A, B, C, D, E. Alright, for the edge, okay, for the edge we have, let's say, E1, E2, E3, E4, E5, E6. Okay, the other side A to B is E1, B to C is E2, C to F is a new one. Never mind, wait. B to D also new. Okay, so we have 6, E7 and E8, E9. Alright, so for the edge E1, we have E1, E2, up to E6. Okay, on the other side, for the V2, we have A, B, C, F, D. A, B, C, D, F. Sorry, D, F. And for the E2, we have E1, E2, E7, E8, and E9. Okay, then when we combine together, we obtain a new graph. So the vertex set for this new graph is V1 union V2. Okay, we can combine together, so we obtain A, B, C, D, E, and we have a new one which is F. Okay, for the edge set E1 union E2, so we combine together all the distinct edges E1 up to E6 comes from the set E1, and we combine together from the set E2. We have additional edges E7, E8, and E9. Okay, so this is a new graph produced by combining two different graph G1 and G2. Representing graph and graph isomorphism. So the first part, representing graph is easy, but for graph isomorphism is quite complicated. So never mind, we go slow, step by step. Okay, so in working with a graph, it is helpful to be able to choose its most convenient representation. Okay, the most convenient representation of the graph. Sometimes two graphs have exactly the same form, in the sense that there is a one-to-one correspondence between their vertex sets that preserve edges. So in such a case, so we say that these two graphs, okay, these two separated graphs are isomorphic graphs, This section shows how to represent graph in several different ways. That's the first part. And the second part is how to determine whether two separated graphs are isomorphic or non-isomorphic. Alright, adjacency list. Adjacency list can be used to represent a graph with no multiple edges. By specifying the vertices that are adjacent to each vertex of the graph. Okay, I give you example. Use adjacency list to describe the simple graph given in the following figure. So I give you one figure. So your task is to describe this graph by using adjacency list. So let's see how to solve this problem. So this is what we say as adjacency list. So we have vertex A, B, C, D, E. So we have A, B, C, D, E. Alright, exactly same as the given graph. Okay, the vertices in the given graph. So for the vertex A, we have adjacent vertices. For A, we have B, we have C, and we have E. Adjacent to the vertex A. For the vertex B, we have only single vertex, which is A. Okay, A. For the vertex C, it is connected to A, it is connected to E, it is also connected to D. So that's why the adjacent vertices to C are A, D, and E. So for the D, it is connected to C and it is connected to E. Alright, for E, it is connected to D, it is connected to C, and also connected to A. So this is the adjacent vertices. Okay, the adjacency list for the given graph. Yes, as usual, this is your most exciting part, okay, in this lecture, which is the quiz, the attendance quiz. So in this question, represent the directed graph shown below by listing all the vertices, okay, that are the terminal vertices of edges starting at each vertex of the graph. Wow, it's quite interesting question. So I wish you all the best. Please solve this problem within 5 minutes and please submit your answer to my email. So I give you some hint. So make sure your table contains two columns. The first column is the initial vertex and the second column is terminal vertex. The first column is initial vertex and then the second column is terminal vertex. So initial means the starting point, terminal means the ending point. Alright. For example, the starting initial vertex A. So what are the terminal vertices? Okay, A ended at. Okay, that's the hint. I'll give you about 5 minutes. Okay, submit your answer to my email. Okay, so now we discuss the answer for this quiz, the answer for this problem. Alright, so as I mentioned before, your answer should consist of a table with two columns. The first column is initial vertex and the second column is terminal vertices. Alright, for the initial vertex A, let's see A. So the terminal vertices means A is moving out. Okay, so the arrow moving out from A. Okay, so we have this one, A to B. We have another one, A to C. And then A to D. And then we have A to E. Alright. There are 4 terminal vertices of the vertex A. Alright, so we are searching for the arrow going outside A. Alright, moving from A. Because A is the initial vertex. So for the case A and B, A is the initial vertex. So B is the terminal vertex. Alright. So for B, again, we are looking for the arrow going out from B. So we have a loop here. Okay, so we have B here. And then we have another one is this one, this arrow, it is pointing to D, so we have D. All right, so finish with B. We move to the next, which is C. So for C also we have a loop, so we have C here, and then the arrow pointing out from C, we have this one from C to E, and then we also have this one from C to A. Right, so we call all the terminal vertices for the vertex C. And then for the D, where is D? Okay, for D, surprisingly there is no arrow pointing out from D. There is no arrow, so the only arrow is pointing into D. Okay, we have this one and this one, so that's why there is no terminal vertices or terminal vertex on D. For E, okay, for E, we have pointing out this one, which is D. We also have this one, which is C, and we have this one, which is B. So we cover all the terminal vertices for each vertex in the given figure, in the given directed graph. All right, I hope all of you can give me exactly the same answer. All right. Okay, the next topic is about adversary matrices. So, what is the adversary matrices? Carrying out graph algorithms using the representation of graph by list of edges or by adversary list can be cumbersome. Okay, it can be cumbersome if there are many edges in the graph. Okay, so previously we're playing with simple graph, so you just have up to maybe 10 edges, but in real application it can be more. Okay, so the process can be cumbersome. To simplify computation, graph can be represented using matrices. So there are two types of matrices commonly used to represent graph. The first matrix is based on the adjacency vertices. Okay, based on adjacency vertices, and the second matrix is based on incidence vertices. Okay, let's see one by one. Suppose G equal to VE be a simple graph, okay, where the cardinality of V equal to n. That means there are n distinct vertices in the vertex set V. Okay, so listed arbitrarily as V1, V2 up to Vn. The adjacency matrix A of the graph G, denoted like this, with respect to this listing of the vertices, is the n by n matrix. N by n matrix with entries 0 and 1. So the entries for this n by n matrix are either 0 or 1. Alright. So the entry is equal to 1. Okay, the entry is equal to 1 as its ijth entry. Okay, the entry for the ijth entry for this matrix A is equal to 1 when Vi and Vj are adjacent. Okay, for the ijth entry for the matrix A, the entry is equal to 1 if Vi and Vj are connected or are adjacent. That means there is an edge connecting this Vi and Vj. So the entry for that ij entry is equal to 1. Otherwise, it is equal to 0. In other words, if its adjacency matrix is AG with entries A, I, J, I is the location for the row, J is the location for the column, then the Aij is equal to 1 if there is edge connecting Vi and Vj. Alright? Otherwise, it is equal to 0. I give you example. Use an adjacency matrix to represent the graph below. So first of all, let's identify the vertices for this graph. So we have A, B, C, and D. Alright? So in the graph, okay, this is the original graph. So we have A, B, C, and D. Similarly, at the column also we have A, B, C, and D. Alright. So at the graph, we refer one by one. Okay, is there any edge connecting A to A? Or in other words, is there any loop at the vertex A? There is no loop, so that means we put the entry equal to 0. Is there any edge connecting A to B? A to B, yes. This edge, so we put the entry equal to 1. Is there any edge connecting A with C? A with C, yes. This edge, so we put this one, the entry for the A 1, 3 is equal to 1. Okay, so for this entry is located as at row number 1, column number 4. Okay, let's see. Is either A and D is connected? A and D, yes. Okay, it is connected by by this edge. So we put the element or the entry is equal to 1. Alright. Okay, move to the second row. Is B and A connected? B and A, yes. B and A is connected. Is B and B are connected? There is a loop at B? No, there is no loop. Okay, no loop. So we put 0. Is B and C connected? B and C, yes, it is connected. So the entry equal to 1. Is B and D connected? B and D, no, there is no edges here. There is no edge here. So we put 0. Alright, next row is C. Is C and A is connected? Yes. Then we put 1. Is C and B is connected? Yes. We put 1. Is C and C is connected? That means, is there any loop here? No, there is no loop. So we put 0. And then is C and D is connected? C and D, no, there is no edge here. So we put 0. And then we move to the fourth row. Is D and A connected? D and A, yes. Is D and B connected? Connected? D and B, no, there is no edge. So we put 0. D and C are not connected. Okay, so we put 0. D and D, is there a loop here? No loop, so we put 0. So this is exactly the same graph that we obtained as the answer. Alright, so I hope you can follow and you know how to form the adjacency matrix. Okay, so in this example we do it in the reverse way. If previously I give you graph and your task is to produce the adjacency matrix. So in this problem I give you the matrix and your task is to produce the graph. Alright, so from the given matrix we know that, okay, the given matrix is 0 1 1 0 1 0 0 1 1 0 0 1 and 0 1 1 0. Okay, and when we put all the vertex A, B, C, and D, okay, because the ordering is A, B, C, D, so A, B, C, D. Alright, so because this entry is 0, that means there is no loop at the vertex A. Because this entry equal to 1, that means A and B are connected. So we put edge connecting A and B. Because this entry equal to 1, that means A and C are connected. Okay, that means there is an edge connecting A and C. Because this entry equal to 0, that means A and D, there is no edge connecting A and D. Okay, we move to the next row. Because B and A is equal to 1, that means there is an edge connecting B and 1. Already one edge there. So we move to the second one. Because B equal to 0, that means there is no loop at the vertex B. Because BC equal to 0, that means B and C are not connected. Because B and D equal to 1, so that means there is an edge connecting B and D. Okay, we move to the for third row, because this entry equal to 1, that means C and A are connected. C and A, yes, we have already an edge connecting A and C, because this entry equal to 0. Okay, so that means C and B are not connected. There is no edge connecting these two vertices. Because this entry is equal to 0, that means C and C, that means there is no loop at the vertex C. Because this entry equal to 1, so that means C and D are connected together. So you put an edge connecting these two vertices. Alright, so we move to this to the final, or to the fourth column of the fourth row. We have this entry equal to 0. That means D and A are not connected. D and A, there is no edge connecting A and D. Because this entry equal to 1, that means B and D are connected. B and D, yes, we already have the edge. Because this value equal to 1, that means C and D are connected. Yes, we already have the edge connecting these two vertices. Because this value equal to 0, that means there is no loop at the vertex D. So finally, this is the complete graph of the given adjacency matrix. Note that an adjacency matrix of a graph is based on the ordering. Chosen for the vertices. Okay, in the previous one, we have A, B, C, D, E. Okay, so in this example, this particular matrix is produced by this ordering A, B, C, and D. Alright, if you use different ordering, let's say I give you D, C, B, A. Alright, the order is D, C, B, A. So we can get exactly or totally different matrix from this adjacency matrix. We can obtain different adjacency matrix. Alright. Hence, there may be as many as n factorial different adjacency matrices for a graph with n vertices. Okay, so previously we have how many vertex? We have A, B, C, and D. That means our vertex n equal to 4. That means there are 4 factorial different adjacency matrix. Okay, the adjacency matrices with 4 vertices A, B, C, and D. Alright, because there are n factorial different orderings of n vertices. Okay, different ordering can give us different adjacency matrix. The adjacency matrix of a simple graph is symmetric. The matrix is said to be symmetric, that is Aij equal to Ji, because of these entries are 1 when Vi and Vj are adjacent and both 0 otherwise. Okay, because if we say that A and B are connected, it is same as we say that B and A also connected. Okay, same. That's why we call the adjacency matrix as symmetric. Okay, or Vi, we say Vi is adjacent to Vj. It is same as we say that Vj is also connected to Vi. Just the same thing. Adjacency matrices also can be used to represent undirected graph. Undirected graph with loops and with multiple edges. A loop at the vertex Vi is represented by a 1. Okay, at the II position of the adjacency matrix. Okay, for loop, so the value for the entry is equal to 1. When multiple edges connecting the same pair of vertices Vi and Vj, or multiple loops at the same vertex, okay, are present, the adjacency matrix is no longer a 0-1 matrix. Previously, the entries only 0 or 1. Alright, so it is no longer a 0-1 matrix, since the ijth entry of this matrix equals the number of edges that are associated to Vij. Okay, all undirected graphs, including multigraphs and pseudographs, have symmetric adjacency matrix. So let's see this example. Use an adjacency matrix to represent the pseudograph shown below. So I give you one graph. So your task is to produce the adjacency matrix. Okay, so previously we have from A to B just single edge, but this time we have triple edges. So let's see how to solve this problem. So the adjacency matrix using the ordering of vertices. The order is A, B, C, and D. So we follow the order exactly: A, B, C, and D, A, B, C, and D. Alright, so how to produce this graph? So as you can see, for A and A, there is no loop, so the value equal to 0. Okay, from A to B, there are how many edges? We have 1, 2, 3, 3 edges. So the value is equal to 3. For A and C, okay, A and C, there is no edge connecting A and C, so the value, the entry for this location is 0. For A and D, there are 1 and 2. There are 2 edges, so the value is equal to 2. Alright. For the B and A, okay, we move to the second row. B and A. B and A. How many edges there? Yes, there are 3 edges. So the entry equal to 3. So for BB, there is no loop. So the entry equal to 0. For BC, B and C, there is only single edge here. So the answer is equal to 1. The entry value equal to 1. For B and D, there is only single edge. So the value for this entry is equal to 1. We move to the third row. Okay, C and A are not connected, so the entry is equal to 0. Okay, from C to B, only single edge here, so the entry is equal to 1. For C to C, because there is loop here, we have loop here, so the entry is equal to 1. From C to D, there are 2 edges, so the value is equal to 2. Move to the final row. D and A, there are 2 edges, so the entry equal to 2. From B to D, single edge, so the value equal to 1. For C to D, there are 2 edges, so the value is equal to 2. And for D and D, there is no loop, so the value equal to 0. So this is the entire adjacency graph for the given graph. The matrix for a directed graph G equal to VE has a 1 in its ijth position if there is an edge from VI to VJ. Okay, for directed graph, the arrow or the direction of the edge is very important. Alright, so from VI to VJ, okay, that means the arrow pointing from VI goes to VJ. Alright, the arrow. Where V1 up to Vn is an arbitrary listing of the vertices of the directed graph. Alright. In other words, if AG equal to AIJ, okay, if the entry for the adjacency matrix is denoted by AIJ, where I is the location for the row, J is the location for the column. So AG is the adjacency matrix for the directed graph G with respect to this listing of vertices, then Aij equal to 1 if there's an edge connecting Vi from Vi to Vj, and 0 otherwise. Alright? 0 otherwise. Okay, for entry Aij, so we consider 2 vertices, Vi and Vj. Because this is a directed graph, so we consider Vi. Okay, because I comes before J, so Vi moving to Vj. If these 2 vertices are connected, there is an edge connecting these 2 vertices with arrow pointing from Vi to Vj, then the entry AI is equal to 1. Otherwise, this entry equal to 0. The adjacency matrix for a directed graph does not have to be symmetric. Okay, for the undirected graph, yes, the matrix is symmetric, but for the directed graph, it does not have to be symmetric because, okay, because if there is an edge from Vi to Vj, there is not necessarily there is an edge from Vj back to Vi. Not necessary. Okay, it can be no edge connecting Vj. Again, if there is an edge connecting Vi to Vj it is not necessary there is an arrow pointing back from Vj back to Vi. Not necessary. Okay, because that is why the adjacency matrix in the directed graph is not symmetric. It depends totally on the direction of the arrows in the given graph. Alright. So finish with the adjacency matrix, we move to the incidence matrix. Another common way to represent graph is to use incidence matrices. Let G equal to VE be an undirected graph. Undirected graph. Suppose that V1 up to Vn are the vertices and E1 up to Em are the edges. Okay, that means there are n vertices and there are m edges in this graph G. Then the incidence matrix with respect to this ordering of V and E is the n by m matrix. N by m matrix denoted by capital M with entries M, I, J. I is the location for the row, J is location for the column, where Mij equal to 1 when edge Ej is incident with Vi. When edge Ej, okay, J is incident with the vertex Vi. Okay, otherwise equal to 0. For example, let's say for M23. Okay, so M23 is equal to 1 if atau or when edge E3, okay, is incident with V2. Okay, as you can see, that is important to identify I and J because it determines the value for the entry Mij. 0 otherwise. Okay. Alright, so let's see what is the difference between adjacency matrix and incidence matrix. So in the incidence matrix, the size or the dimension for the matrix is m by n. What does it mean? That means the row, okay, we have the vertices as the row and we have edges as the columns. Alright, because we have n rows and we have m columns. Alright, so the vertices becomes the row and edges becomes the columns. Okay, so this is the incidence matrix. I'll give you one graph and produce the incidence matrix. Okay, so we follow the order. Okay, based on the definition, the order is V1 up to Vn, E1 to up to Em. So we have V1 up to V5, E1 up to E6 based on this order. Alright, so let's check one by one. For M11, okay, this one M1. Okay, let's see V1. V1, yes, it is incident with the vertex E1, so the value equal to 1. Okay, V1 with E2. Okay, where is E2? Yes, this is E2, so it is also incident with E2, so the value equal to 1. Okay, so V1 with E3. Okay, so there is no E3 is incident with other vertices but not V1, so the entry equal to 0. So same goes with E4, also equal to 0. E5 equal to 0 and E6 equal to 0. Since V1 only incidence to E1, since V1, the vertex V1 is incidence only with the edges E1 and E2, so we have 1 at this entry and 1 at this entry only, while the other entries equal to 0. Okay, we move to the second row, which is V2. V2 with E1. Okay, there is no edge E1 connected to the vertex v2, so the value equal to 0. So same goes with the vertex with the edge e2. Okay, e2 also not connected, not incident with the vertex v2, so the answer, the value for the this entry equal to 0. So v2 with the edge e3, yes, edge e3 is incident with the vertex v2, so that's why the entry equal to 1. Okay, so e4 also incident with the vertex v2, so the entry is equal to 1. Because e5 is not incident to the vertex v2, it is equal to 0. So because e6 is incident with the vertex v2, the entry equal to 1. So we continue the same process until we cover all the vertices and all the edges. So finally we can obtain this complete incidence matrix. Incidence matrices can also be used to represent multiple edges and loops. Multiple edges are represented in the incidence matrix using columns with identical entries because these edges are incident with the same pair of vertices, while loops are represented using a column with exactly one entry equal to 1 while the other entries equal to 0, corresponding to the vertex that is incident with this loop. I give you example. So this is the incidence matrix, okay, where we have a loop. Also we have multiple edges connecting to vertices. Okay, so previously we have two vertices connected by using single edges. So this time we have multiple edges. We also have loop. Okay, let's see how to answer this question. So for the first row, v1, what is v1? So we have a vertex, we have a edge e1, okay, incidence with it, so the entry equal to 1. v1 to e2, yes, there is an edge also incidence with v1, and v1 with e3, yes, there is an edge e3 incidence with the vertex v1, so we have 1 and 0 for the other edges. Alright, move to the second row, v2. So for the row v2, for the vertex v2, it is incidence to how many edges? e2, e3, e4, e6, and e7. That's why we have 1 at e2, e3, e4, e6, and e7, while the other edges equal to 0. For the vertex v3, where is vertex v3? Yes, vertex v3, it is incidence to e4 and e5. So it is equal to 1 at e4 and e5 and 0 at the other edges. For the vertex v4, it is incidence with the edge e7 and a loop e8. So we have 1 at e7 and 1 at e8. And for the vertex v5, where's the vertex v5? It is incidence with the edge e5 and e6. So we have 1 at e5 and e6 and 0 at the other edges. So we have the complete incidence matrix for the given pseudo graph.